Okay. So for example here عم نشوف إنه we will compare different treatments near the wall. Okay. So first إذا ما بنستعمل wall treatment near the wall, what we have is the following. Or if we are just not using the non-equilibrium wall functions, عندنا problem إنه in general we have a condition on y plus values, and it was shown إنه the y plus value should be between 30 and 300 to 500, and because of this condition ما حقدر ألقط what is happening here in this region. So this will make this region not well predicted, okay? لأنه عندي constraint على y plus value that I can put, and then I have a problem in capturing the effect near the wall. So this is why in this case plus إنه أنا عندي restriction على mesh expansion ratio which should not be larger than 1.2. يعني شو هو expansion ratio؟ أنتوا بس تعملوا meshing if you remember قلنا انه اذا بدنا نعمل growth of cell size ما فينا نعمله very steep. يعني ما في يكون عندنا let's say if I take cell size I plus 1 over SI size of cell I, ما لازم الريشيو يكون كتير كبير. It should be below 1.2. okay. So this restriction will require having higher number of cells to do transition from the wall to the outer region. And this is why in this case the prediction of physics near wall is not well trapped. From here I need to introduce the enhanced wall treatment option. The enhanced wall treatment option will allow me to combine a blended law of the wall and a 2 layers on mode. So the idea is because this region is not resolved, okay, وحتى إذا بدي أعملها if I want to resolve it أول شيء y plus value it's not recommended وطيهم كتير لأنه كcomputation بصير في non accuracy, plus ثاني limitation إنه إذا كتير بصغر y plus value بصير I need a lot of elements to resolve this region and to do good transition من wall region to the outer region. This is why the implementation of law of the wall to my CFD will help a lot into do the transition from the near wall region to the outer region. So the enhanced wall treatment option will combine a blended law of the wall and a 2 layers on model. It is suitable for low Reynolds flows or flows with complex near wall phenomena. K epsilon turbulence models will be modified for the inner layer in order to account for wall effects. Generally, it requires a fine near wall mesh capable of resolving the viscous sublayer down to y plus equal to 5 and a minimum of 10 to 15 cells across the inner layer. In this case, the viscous sublayer, the buffer layer, and the log low layer can be resolved. Okay. So whenever I use the enhanced wall treatment option, I can go for y plus value that are lower. Yani already I can trap what is happening. Plus I can implement the models I developed empirically to assess what is happening in this zone. And as you can see, I can do gradual increase in size to take into account the transition from wall region to the outer layer. From here, the importance of introducing the enhanced wall treatment option to CFD. Now, in summary, wall functions are still the most affordable boundary treatment for many industrial CFD applications. In the K epsilon family, scalable wall functions is the recommended setup option to model what is happening near the wall. Standard wall functions works well with simple shear flows, and non-equilibrium wall functions will improve the result for flows with stronger pressure gradient and separation. The enhanced wall treatment is used for more complex flows where log low may not apply. So as I told you, even in the wall treatment, you have several empirical relations. depending on the application you have. You know, whenever you have new effects like pressure gradient, separation, etc., you need to modify the wall function to be able to be suitable for your application. So you have improvement of wall functions in case you have flows with stronger pressure gradient and separation issues. In addition, enhanced wall treatment is used for more complex flows where log law may not apply. So for example, for non-equilibrium wall shear layers or in the bulk Reynolds number, in zones where the bulk Reynolds number is low. Now, what are the boundary conditions required? We have seen together, if you remember, when we introduced turbulent boundary layers, they told us, let's say, introduce the hydraulic diameter, introduce the length scale, etc. So here we'll show what are the type of inlet boundary conditions required for turbulence modeling. So when turbulent flow enters a domain at inlets or outlets, boundary conditions for K, epsilon, omega, and or Reynolds stresses must be specified depending on which turbulence model you select. So if you select K epsilon, for example, you can see corresponding inputs whenever you enter inlet or outlet. They will ask you for input conditions, inlet conditions related to K and epsilon. So 4 methods for directly or indirectly specifying the turbulent parameters. We have first, the explicit input will be to enter the turbulent kinetic energy, dissipation rate, or omega, or Reynolds stress component, depending on which model you select in the turbulence models. Plus, if you remember, for example, when we did the example on the rooms, the ventilated rooms, they asked us to introduce the turbulent intensity, and we had the option or to introduce turbulent intensity plus length scale, or to introduce turbulent intensity plus hydraulic diameter. Okay, so this is another option. This is the one we use together in our application of ventilation. So 1 second, sorry. Okay, so the second option, as we said, so or we introduce the turbulent intensity and length scale, and in general, length scale is related to size of large eddies that contain mass of energy, and this is measured experimentally. Yani you should measure it in order to implement it to your CFD, or you can take typical values from literature data. So for example, for boundary layer flow, it's equal to L times 0.4 delta 99. What we mean by delta 99 here is when you have the boundary layer development, it's the thickness of the boundary layer when it is developed at 99%. Okay, so you know that whenever you have a boundary layer, the thickness of the boundary layer will increase as you go over the surface. Okay, so you can like measure like a certain thickness whenever you reach nearly a flat state. So you can consider that this is a 99% of the thickness. And for flow downstream of grids, you can consider that the length scale is nearly equal to the opening size. Now, another option, and that is widely used for internal flows, is to specify the turbulent intensity and the hydraulic diameter. So for example, when we had an inlet and we want to specify boundary conditions for turbulence, turbulence intensity is a parameter, okay, that can be measured experimentally, as I told you, and or can be found as related to the turbulence level of the flow, and can be found in literature data. So you can introduce it. And for the hydraulic diameter, you know how to calculate it. You have a certain area. For example, if we have a rectangle, we know that DH is equal to 4A, where A represents the cross-sectional area, over the wetted perimeter P, which represents the total length of contact between the fluid and your inlet. Also, another possibility is to introduce the turbulent intensity and viscosity ratio. This will be the case if you are dealing with external flows. Now here we will summarize, if you want, in this slide, we will summarize the different models and the characteristic of each of these models. So first, we have, as we said, the Spallard-Almaraz model. It's in which a single transport equation model solving directly for a modified turbulent viscosity. It's designed specifically for aerospace applications involving wall-bounded flows of a fine near-wall mesh. Fluent's implementation will allow the use of the coarser meshes, and we have option to include the strain rate in K production terms to improve the prediction of vertical flows. Of course, you don't have to memorize any of these. These are for you, for your knowledge. So whenever you have an application and you want to decide which turbulence model to use, you can refer to this table. Concerning the standard K epsilon model, as we discussed before, the main modification is that we are introducing now a new equation, and we are introducing a relation between turbulent kinetic energy and strain rate dissipation rate of energy epsilon. So we have the baseline two transport equation model is to solve for the two variables of turbulence K and epsilon. This is the default K epsilon model. The coefficients in the standard K epsilon model, as we discussed, are empirically derived. So we use experiments to come up with constants used in the differential equations of K and epsilon. And it's valid for fully turbulent flows only. Options to account for viscous, heating, buoyancy, and compressibility are not present in standard K epsilon model. This is why whenever you have any of these effects, it's advised to not use the standard K epsilon model. Now, another variation of the K epsilon model is the renormalized group K epsilon. We said that in this case, the equations and coefficients are analytically derived using a certain theory called renormalized group theory. Significant changes will be performed in the epsilon equation, and this will improve its ability in modeling highly strained flows. And in addition, we have additional options that can be implemented to predict swirling and low Reynolds number flows. Another option of K epsilon is the realizable K epsilon, and this model is mainly characterized by changes that will allow certain mathematical constraints to be obeyed, and therefore will improve the performance of standard K epsilon. We have seen, for example, that the realizable K epsilon model will give good prediction for case, let's say, of rounded jets, or when we have rotational effects, which will not included in the standard K epsilon model. Now, we mentioned that a standard K epsilon model in general is good for fully turbulent flows, so for high Reynolds numbers. But what if we have an application with relatively small Reynolds numbers? We have seen that the standard K omega can be an option. It's also a two transport equation model now that will relate K and omega. Omega is the specific dissipation rate, as we mentioned before, and it's related to the ratio of epsilon over K based on Wilcox scientists. Now, this model shown superior performance for wall-bounded and low Reynolds number flows, as we mentioned, and it shows also potential to predict the transition between different zones. Now, this model was shown to have good performance whenever we have free shear and compressible flows. Now, as we mentioned, whenever we have in the same problem regions characterized by relatively low number and other regions with high Reynolds numbers, we can use the SSTK omega model, which will implement a function for gradual transition from low Reynolds number to high Reynolds number. So another variant of the standard K omega model is the SSTK omega. It combines the original model for use near walls and the standard K epsilon model, which is advised to use far from walls. And this can be done by implementing a blending function that will allow the gradual transition from K omega to K epsilon. It also limits the turbulent viscosity to guarantee that we have better prediction of the system. And in this case, the transition and shearing options are borrowed in order to take into effect more complex scenarios as shear effects and transition from low Reynolds to high Reynolds. The disadvantage is that we don't have an option in SSTK omega to include compressibility effect. So if we have compressibility effect, it's not advised to use this model. Finally, concerning Reynolds stress model, Reynolds stresses are solved in this case directly using the transport equation, avoiding isotropic viscosity assumptions of other models. So whenever you have high anisotropy, it's suggested to use the Reynolds stress model. This model is used for highly swirling flows, for quadratic pressure strain option, which will improve also the performance for shear flows. So this is in summary the characteristic of the different models we have considered. Now, concerning the behavior and use of these models also will summarize their main application in the following table. First, for the Spallert-Almaraz model, it's an economical model for large meshes. So if you have very large, if you want mesh, you have a big space, and you don't want to come up with a very, very high number of elements. One option for turbulence modeling is the Spallert-Almaraz model. It is performing poorly for 3D flows, free shear flows, flows with strong separation. So whenever you have one of these applications, don't use it. It's suitable for moderate complex scenarios in 2D, including external internal flows and boundary layer flows under pressure gradients. So for example, this model is suggested to be used for airfoils, for wings, for missiles, and for ships. Concerning the standard K epsilon, it was shown to be highly robust. It's widely used despite the known limitation of this model. It performs poorly, as we said, for complex flows involving severe pressure gradient, separation, or strong streamline curvature, while for many engineering applications, like for example, ventilation applications, where you don't have round jets, it's good to use it. It's suitable for initial iterations, initial screening of alternative designs, and parametric studies. Sometimes we start with the standard K epsilon, and then we move to more complex scenarios after. So it can be used as transition turbulence model because convergence is relatively easier with it. So just when you can initiate your run with standard K epsilon, and then move if you want to more complex turbulent flows. Concerning the renormalized group K epsilon, it's suitable for complex shear flows involving rapid strain, moderate swirl vortices, and locally transitional flows. For example, we can use it whenever we have boundary layer separation, whenever we have applications where we have massive separation of flows and vortex shedding behind the bluff bodies. If you remember, when we consider wind tunnel application and you have separation and formation of vortices and wake region behind the object, here, for example, it can be better to use the renormalized group K epsilon. So we can use it, for example, to study the stall in wide angle diffusers, or in room ventilation, it's suitable also. Now, concerning the realizable K epsilon, it offers largely the same benefits and has similar application of the renormalized group, but it's possibly more accurate and easier to converge. When it's working well, the realizable is advised because it converges easier than the renormalized group. Now, concerning the standard K omega, it has shown superior performance for wall-bounded boundary layer, free shear, and low Reynolds number flows. It's suitable for complex boundary layer flows under adverse pressure gradient and separation. which is the case for external aerodynamics and turbomachinery applications. It can be used for transitional flows, though it tends to predict early transition. So this is one of the limitations. Separation is typically predicted to be excessive and early in standard K omega. We can improve this using SSTK omega, in which the dependency on wall distance make it less suitable for the case of free shear flows. So as you can see, each model represents advantages and disadvantages, and it's recommended for certain applications. So depending on the application you have, you can select the convenient model. Now concerning
عندنا
the
heat exchanger أي موديل بنستعمل؟
هلا الهيت exchanger مثلا you can use realizable K epsilon for it. Okay.
اوكي
It will work fine.
دكتور، وكنت عم تقولي انه الكي والابسلون هول الكونستنتس بنجيبهم امبيريكلي، مظبوط؟
نعم، في بروبلم هلا اكيد نحن ما حنجيبهم، هن implemented بانسس، بس تنفهم هن كيف اجوا. في اذا عم نشتغل بحسب الموديل، اذا عم تشتغل رينا رامالايزد جروب هول الكونستنت ديرايف اناليتيكلي، واذا عم تشتغل ستاندرد كي ابسلون هول الكونستنت ار derived empirically. يعني كل موديل عنده appropriate derivation of these constants.
اوكي دير.
Okay. Now, concerning the Reynolds stress model, it represents the most sound Reynolds model. يعني هو one of the best Reynolds stress model, but the disadvantage it will take higher computational time. It avoids isotropic eddy viscosity assumption, but we need more time, more computational time, and higher memory is required. هلا عادة بالابليكيشن اللي نحن بنستعملها بالسي اف دي لاب realizable K epsilon will work well. Okay, so I advise you to use it. إلا إذا your application يعني فيها عندها recommended model غير، يعني إذا your application is characterized by certain issues، وهون بهذا التيبل أعطونا إنه recommended to use something else, use it. بس for the majority of applications that we are dealing with, realizable K epsilon is fine. اوكي. هلا فور اكزامبل الرينولد ستريس عنده ادفانتج انه ما بيعتبر assumption انه في isotropic eddy viscosity, so it can take into consideration anisotropy of the flow. This is why it's very accurate, especially in applications, for example, like 3D flows with strong streamline curvature or strong swirl and rotational effect. And for example, if you have a curved duct, if you have a rotating flow passages, or if you have swirl combustors with very large inlet swirl, etc. Okay. So this is the behavior of the models we have suggested until now. You still have a lot of other models. Here, for example, we show you the equations used for K epsilon and for other models. So as you can see here, for example, whenever I use K turbulence modeling, I need an equation for epsilon and an equation for K. We already introduced in previous slides the equation for epsilon. Also, we can develop similarly a turbulence kinetic energy equation that is used to solve for the kinetic energy variable. And as you can see, K and epsilon are related to the fluctuation of the flow and to the eddy viscosity. Okay, so we need to predict this term, which is called the rate of production, in order to be able to solve for K. So this is why we can consider that this term can be modeled, can be related by this equation to K. So once you solve for K, you can actually determine the production rate. So the production actually refers to the rate at which kinetic energy is transferred from the mean flow to the turbulent fluctuations. Pk is the turbulent stress times the mean strain rate. So physically, it's the rate of work sustained by the mean flow on turbulent eddies. As you can see, to model P, you need to know, you need to acknowledge for the presence of Reynolds stress components and model the fluctuating component U prime average. Okay. So this equation will relate K to this Reynolds stress. And when by closing your equations, you can solve for the variation of the fluctuating component. Now, the dissipation rate definition is as follows. So the dissipation rate is related to the Reynolds stress, okay, times the eddy viscosity. So as you can see, all of these parameters defined, epsilon and K, will be related to the fluctuating component. This is why when we solve for them, we'll be able to compute the stress terms, okay? So physically, turbulence kinetic energy is produced due to the mean flow gradients and is dissipated by viscous effects. Imbalance between the production and the dissipation will cause then K either to grow or to decay. The last term in the K equation is a diffusion term, and it's modeled by a gradient diffusion assumption or Reynolds analogy. From here, we use a turbulent Prandtl number in the diffusion term. I know that these ideas are relatively complex, but just I want you to see that how we can relate the component of the stress model to turbulent variables like epsilon, K, and the eddy viscosity. So when we solve for these, we will be able to predict the tensor of Reynolds stresses. Now, we have also another type, which is one of the most complex, if you want, turbulent modeling, who will direct numerical simulation. And as the name indicates, we have in direct numerical simulation, we actually we solve the equations of Navier-Stokes in certain zones. And this will require a very high computational time. So in direct numerical simulations, the 3D unsteady Navier-Stokes equations are solved numerically by resolving all scales, both in space and time. And this makes the computation really challenging. So for simple geometries and at modest Reynolds numbers, direct numerical simulation has been done successfully. So for example, for a simple turbulent channel flow between two plates, we were able to solve for the Navier-Stokes equation with space and time. But when we say direct numerical simulation, so this is equivalent to a numerical wind tunnel for conducted more fundamental turbulence research. So we are trying to get an analytical solution for Navier-Stokes equation. And as we said, this is not always applicable and it will take a lot of time. So for practical engineering purposes, direct numerical simulation is not only too costly, but also the details of the simulations are usually not required. Instead of taking a lot of time and having, if you want to resolve analytically by detail how the Navier-Stokes equation, we can, and this is not always possible also. As we said, in a lot of engineering application, it's not possible to have a direct numerical solution for the equation. This is why we decided that sometimes we can, for part of the flow, solve analytically the Navier-Stokes equation, and for another part, which is more complex, to use other techniques, okay? So we have two general engineering approaches to modeling turbulence, which is related to direct numerical simulation, but not, we do the full domain, we solve it using DNS. So when you say DNS, as I said, this consists on solving the Navier-Stokes equation for all turbulent scales, which will not always be possible. It's possible for limited applications. From here, the idea is, let us find regions where we can use direct numerical simulation, and for other regions, we use other models. So the two general engineering approach will be a large eddy simulation and Reynolds averaging Navier-Stokes models. So the idea is that for large eddies, if you remember when we talked about turbulence, we said that you have large eddies and small eddies. For large eddies, direct numerical simulation is possible, while for small eddies, it becomes more challenging. This is why the idea of large eddy simulation is to do separation of zones. In some zones where the numerical solution is possible, the direct numerical solution is possible, we do it. And for other regions, we can use other turbulent models that were developed before to treat such complex regions. So from here, we can, if you want, let me show you the idea of large eddy simulation. I will, as I told you, will not go over the details of equation solution, but we should know the properties of the flows. Just here to understand in overall what is large eddy simulation. So as you can see in this graph, the idea is that in turbulence, the instantaneous component of velocity is divided into two components: an average value and a fluctuating component. Okay, and the idea of large eddy simulation is that the spectrum of turbulent eddies in the Navier-Stokes equation will be filtered. So we'll divide eddies into two parts: large eddies and small ones. Okay, so the filter of eddies will be function of the grid size, and eddies smaller than the grid size will be removed and modeled by a subgrid scale model, which can be any one of the models we developed before, while large eddies will be directly solved numerically by the filtered transient Navier-Stokes equation. So this means that we'll choose eddies that can be resolved analytically with the direct numerical simulation, and other small size eddies which are more complex and we cannot find for them a direct numerical solution. We can solve them by combining direct numerical simulation performed on large eddies with any of the turbulence models developed before for small eddy scales. So this is the idea of a large eddy simulation. So we filter, this is called filtering of Navier-Stokes equations. So we remove, if you want, all small eddies, and we keep large eddies that can be solved for. And then we can have a differential equation to be solved for the filtered part. And for the remaining part, where we have more complex issues, we can use previous turbulence model developed. And of course, this method will present higher accuracy, because direct numerical simulation at the end is the most accurate way. If you can solve analytically the equations you have, you will get an exact solution. While whenever you develop turbulence models, you will have certain error, okay? And you have to develop several models to be able to approach the problem and have high accuracy as much as possible. So by using large eddy simulation, you can guarantee that for large eddies regions, you have a very good prediction of the flow behavior. And then for just small eddies regions, you can treat them by the turbulent models you developed before. So this is mainly the idea of large eddy simulation. So to summarize, large eddy simulation has been most successful for high-end application where the RENS model failed to meet the needs. As I told you, when you do a turbulent model, you will always have some limitations. It will not be able to predict some issues. So this is why large eddy simulation can be a solution in some cases, because it has been shown to give high accurate results in regions of large eddies. So for example, if you consider applications as combustion, mixing, or external aerodynamics, large eddy simulation was shown to be very accurate. Now, in order to implement large eddy simulation in Fluent, you need to use LES in combination with subgrid scales that will solve for small eddies. Now, for small eddies, you have several options, okay? You can use, let's say, the models developed before, including, let's say, for in case you have detached eddy simulation model, you can use RANS or SST models that we talked about before, or the renormalized K epsilon, okay, or the realizable K epsilon. Also, you can introduce new subgrid scales models that are specific to model regions of small scales, like, for example, wall adapting local eddy viscosity model or dynamic kinetic energy transport model. So you have a lot of other models that can be included to treat subgrid scales. Now, large eddy simulation is compatible with all combustion models in Fluent. Basic statistical tools are available in large eddy simulation. You can do time average and RMS values of solution variables. And also, before running large eddy simulation, you should read more about what are the best practices for large eddy simulation, because it requires specific meshing and meshing treatment, subgrid model, and numerics, plus appropriate boundary conditions. So the more complex is the turbulent model, the more time you will need, and you should, for each model, you should be familiar with its characteristics, in which case it will perform in a good way, in which case it will present poor results, so you can replace it by another model. Okay, so to summarize, this chapter was intended to give you guidelines on the selection of a turbulence model that will be suitable for your CFD simulation. Any question?
يعني نحن أكثر شيء بيهمنا إنه حسب الأبلكيشن أي موديل بدنا نستعمل وهيك
100% صح. يعني انتوا هي الايديا من هذا الشابتر انه تفهموا شوي different options given by Fluent. يعني انتوا بس فتحنا انا وياكم الويندو اوف turbulent models، اجى عندنا كثير مودلز، ما كنا نعرف انه ليش في هالقد مودلز وشو الفرق بيناتهم. So the purpose of this chapter is just to get an overview of the different models, in which applications they are used, just also to understand a little bit إذا بدكم equations اللي بيستعملون من دون without going into their details، لأنه they are very complex equations و as I told you the constants طبعا to derive them it was a very challenging work and it required a lot of research. مثل ما شفتوا في عدة techniques to get these constants، من empirical relation لل renormalized theory etc.
اوكي دكتور.
Okay. Any other question? Okay, thank you. So as I told you, I will upload for you a file, PDF file specific for averaging of Navier-Stokes equations, but please, I advise you to go back to the videos and take notes. لأنه in the notes, I developed for you details. In the PDF, ما فيها هالقد details قد ما عملنا سوا بالderivation. Okay, so I will post the PDF as a reference for you, but try to go over the derivation we did together again to be familiar well with the averaging technique, because you are responsible. And I can give you any differential equation and tell you give me the averaging of this equation. Okay, and averaging is related to turbulence, and whenever you have turbulence, in order to see the effect of turbulence, you do the averaging of the equation. And in this PDF, you can see the different turbulent models and their applications.